Okay, I'll begin. So welcome to this week's Community Zoom, the Green Bay Observatory Community Zoom. I'm Jim Jackson, the director of the observatory. Just a few words about the observatory this year. I just wanted to congratulate everyone. You know, this is the last week of the calendar year. A lot of people going on vacation and a little bit of retrospective. So the retrospective that I would like to highlight for Green Bank is their ability to keep the telescope up and running despite the many challenges we all faced with the pandemic. Hats off to the observatory staff and the team for keeping the observatory functioning and running and taking data for the entire year. I got a lot of exciting scientific results during the course of the year. We're going to talk a little bit about one of them today. The other thing I'd like to mention is that for those of you who submitted proposals to that special call for proposals for the low frequency large programs, thank you very much. We received 10 such proposals. We will be evaluating them as quickly as we can, and you should hear from us by mid-January what the disposition of those proposals is. So thank you for submitting those proposals. And now I'll pass it on to Jay Lockman.
Hey, thanks, Jim. Our speaker today is Haley Wahl from West Virginia University, and she'll be talking about the NANOGrav 12.5-Year dataset, Polarimetry, Faraday rotation, measures from observations of millisecond pulsars with the GBT. And if you have questions, please use the Q&A boxes down in your lower right-hand corner of the screen, and we'll deal with those at the end of her talk. Okay, Haley, take it away.
Great, thank you so much for that introduction. I'm going to share my screen. Oop, that's the end. Okay, let me get to the beginning here. Alrighty, thank you so much to everybody at Green Bank for the invitation. I'm really excited to be talking to you about most of my thesis work, which involves millisecond pulsars and rotation measures and such. This work was done in collaboration with the NANOGrav collaboration and my advisor, Maura McLaughlin. So first of all, what is a pulsar? I'm going to try to break that title down for you. So a pulsar, in case you don't know, is a super dense magnetized neutron star that spins at incredible speeds. It's like taking something the mass of the sun, crushing it down to the size of Manhattan and spinning it as fast as a blender. So pulsars emit radio waves as their light flashes past Earth. So if you look at this GIF, you see that as the pulsar beam is passing by us, we map the energy versus the phase. And so just the brightness, and we make what's called an average profile. And so I'll show you a couple of these, but it's just the energy of the pulsar as it spins around. So pulsars are very precise rotators. They rival atomic clocks in terms of precision. There are two types of pulsars. There is canonical, or well, what I will refer to as regular, normal, slow pulsars. They're all kind of interchangeable. And they have periods of anywhere from about half a second to about 20 seconds. And then there are millisecond pulsars, which are the recycled pulsars, which have periods around milliseconds. So they spin more than 250 times per second. So these are really extreme objects and do really crazy things. So I'm going to be talking a lot about polarization, but just as a basic intro to polarization, if you've ever heard the term polarized or polarization, you might have heard it with respect to sunglasses. And so what polarized sunglasses do is they filter out some of the light so that it reduces glare. And so if you have light that's going in all directions, so the waves can be vibrating parallel and perpendicular to the highway, for example, if you're driving, then what the polarizer in the sunglasses is going to do is it's going to filter out some of those waves so that you're only getting the waves in one direction. And so that's exactly what happens in space to light. So polarization constrains the vibration of the light. So we have linear polarization here, and you can see that the fields here are all kind of going every which way and the light's coming from everywhere. And then this polarizer is going to restrain it to one direction. So you can have two types of polarization. You can have linear polarization, which is just vibrating on a plane, and then circular, where the EM field stays at a constant magnitude and just rotates in a plane perpendicular to the light. And so you can have circular, you can also have elliptical, which is similar. So pulsar light is polarized, and that happens because of the magnetic field of the light. It'll get Faraday rotated, and the magnetosphere will polarize the light, creating a unique polarization profile, as I'll show you, for different pulsars. And it will also become partly polarized as it goes through the interstellar medium, which I will also talk about. So pulsars can have both linear and circular polarization. So in these plots, the black is the total intensity, the red is the linear polarization, and the blue is the circular. And so you can see this doesn't have a whole lot. There's some here, not really much here. This is almost totally linearly polarized, and they are different for each pulsar, just like the average profiles, which is this main component. So rotation measure is a quantity that we measure as the light from a pulsar goes through the interstellar medium. And so you're going to have the light from a pulsar here. It's going to be in some direction, and it's going to go through this medium with this magnetic field B at a distance d with this constant. And the magnetic field of the galaxy, or just the interstellar medium, whatever it goes through, it's going to slightly rotate it. And the amount that it rotates is called the rotation measure. So if you want to quantify it, it depends on a whole bunch of constants like the charge of the electron, the mass of the electron, the speed of light, and the distance that it travels, the electron density, and the magnetic field. Pay attention to that. So the dispersion measure is also a quantity that we can measure as the light goes through the interstellar medium. So the dispersion measure is the integrated column density of the free electrons between the pulsar and the observer. So the expression is here, and it looks a lot like the rotation measure equation. It has the electron density, it has the distance and such. And so if we compare these side by side, you'll notice that the main difference between these two is the magnetic field and this constant, which turns out to be close to 1. So if you divide the rotation measure by the dispersion measure, you can get out this magnetic field, the average magnetic field along the line of sight of the pulsar, and that's going to be in microgauss. And so that's how we can probe the magnetic field of the galaxy, just by looking at the dispersion measure and the rotation measure. So the goals of this project were to, first of all, polarization calibrate NANOGrav's data, which had not been done fully. It had been done for Arecibo before, but take Green Bank telescope data and do that. And the science goals are twofold. The first one is to use the profiles to learn about the pulsar emission. And the second is to use the rotation measurements to learn about the medium that the pulsar light traveled through. So the data set that we're using is from Green Bank, and we're mainly in the data that we use is from Guppy. We have 23 millisecond pulsars, which are from NANOGrav's data set. We have 2 frequencies, 820 megahertz and 1500 megahertz, just NANOGrav's typical observing bands. And we have up to 4 years of data for each pulsar. So you may be saying, but wait, it's called the 12.5-year data set. So first of all, we don't use any gas data. We're just focusing on Guppy data. So that takes away some of the data. And then there was this issue with the sampler board. Some of you here might know a little bit more about this than I do, but the crux of it is that somewhere around 2014, there was a sampler board switch for Guppy. And so the time alignment between the X and the Y polarization samplers became really unstable at some point. So this doesn't affect pulsar timing, which is the main job of NANOGrav because we only use a total intensity, but it did affect the polarization. So if you measure the rotation measures after everything's calibrated, you can see pretty much exactly where the sampler board switch, because you see that the rotation measures go pretty crazy. It's about right here. And so we didn't think that those were very reliable. And so we did not use them. So we cut our data right here, which left us with about 4 years of data. And we found that we couldn't recover these observations. So we just unfortunately had to throw them out. So all NANOGrav data goes through a basic flux calibration and a basic polarization calibration, but a more robust polarization calibration is needed to really study the polarimetry of pulsars. So when the light comes into the telescope, it's slightly altered by the receiver. The light can be quantified by the 4 Stokes parameters. So I, which is the total intensity, Q and U, which make up the linear polarization, and V, which makes up the circular polarization. So when these come in, the measured Stokes parameters are the intrinsic Stokes parameters times this Mueller matrix. And so this Mueller matrix is essentially the telescope's response. So it corrects for the instrument's response for the light. And so in order to get out those intrinsic Stokes parameters from the pulsar, we need to solve for this Mueller matrix. It's a little bit complicated. I'm sorry for, for the giant matrix, but just to get a view of what this is like. So you have different elements in here, and you have different parameters such as the magnitude of the cross coupling, the phase of the cross coupling of the receivers, the differential gain, and the differential phase of the receiver. And so once you correct for this Mueller matrix, which is all done in software called PS Archive, you can get out that intrinsic light from the pulsar. So our calibration method involves taking different observations of a stable pulsar in different days. So we calculate the solution or the Mueller matrix for each epoch. Epoch, I will use the words epoch and day interchangeably. And we take those and then we apply the solution that's closest to each NANOGrav observation to calibrate the data. We fit the rotation measures, and then we add all of those observations together to create a composite profile. So we do it a little bit differently for the frequencies based on the data available. So we took for 820 megahertz, we took long tracks of B1929 plus 10 observations. B1929 plus 10 is very bright, and it has very stable and well-known polarization properties, and so that's why we used it. We took it at 5 different epochs, and for 1500 megahertz, we didn't have long tracks of 1929 plus 10, and so we used one solution that was made from J1022. So what we found, this was the only data that we really had available, but we found that the telescope's response doesn't really change day to day. I mean, it does a little bit, but not an overwhelming amount, which is why we could get away with using these 5 epochs to calibrate about 4 years of data. And when we applied the one solution of 1022 to the data, we found that the observations are fairly constant and that they match those in the literature. So we were pretty confident that that one solution was giving us the correct answers. So the result was gorgeous profiles. NANOGrav has a really long baseline for their data, and so we can get a lot of data and very high signal to noise. So we have Pulsar J1614 here, 1918, and 2302. And so what you're seeing on the bottom is the average profile. What you're seeing on the top is the degree to which the linear polarization angle is rotated. So these are super nice results from it. So part 1 that we're going to do, that I'm going to talk about, is the emission study. So what we have the polarization profiles. What do we get from them? So one of the most exciting things was microcomponents. So when you look at an average profile, you expect that the emission is coming from only one place in the pulsar, and so just this pulsar beam, but you don't really expect it to come from anywhere else. It's fairly localized, other than a couple of different pulsar phenomenon. So the microcomponents are very small components, less than about 3% of the intensity of the highest peak. These microcomponents had been found before, but we discovered 4 new ones in pulsars. For example, I believe we discovered this one in 1455. You can see that the max flux of this pulsar is about 40 millijanskis, but this is less than 1, and so they're really, really tiny. This one occurs over here. You can't really see it. There are varying degrees of polarization. Some are totally linearly polarized, some are not polarized at all. And this shows that pulsar emission can occur over a wide area. So it's not just localized to this beam. Frequency evolution is big when you're talking about pulsar emission. Canonical pulsars or normal pulsars evolve according to Rankin's core double cone model, which makes specific predictions about the number of components in the average profile that will occur as the pulsar, as you go up in frequency. And so there was a paper in 1988 that looked at those, that looked at the number of components in millisecond pulsars and found that they don't always follow that. And ours actually show very little frequency evolution. So this points to the fact that millisecond pulsars are different from canonical pulsars. And the last polarization aspect that we studied was the polarization angles. So as you go through the beam of regular pulsars, the standard, it's called the rotating vector model. The standard that you'll see is this S-shaped curve. And so as you go through the beam, that's pretty much the usual of what you see. Millisecond pulsars show very complex polarization angle swings. You can kind of see an S right here, not really, but this is just an example of one of our profiles. And you can see that doesn't look like a very simple S shape. It looks really complicated. And so this just showed that the polarization angle is very difficult to fit in millisecond pulsars, and that we need a more complex magnetic field structure to fit them. So next, I'm going to talk about the interstellar medium studies that we got from rotation measures. So the goal was to calculate the magnetic field using the fitted rotation measure and the dispersion measure that NANOGrav measures almost every epoch. And so we took the DM closest to that epoch and combined it with the RM to yield the magnetic field. So we use a least squares fitting algorithm and fit for a linear trend, a sinusoidal trend, and a linear and sinusoidal trend. So a linear trend would indicate the motion of the pulsar through a region of increasing or decreasing magnetic field. A sinusoidal trend, especially one of a period of about a year, would indicate clumps of magnetic material along the line of sight, and linear and sinusoidal will point to a combination of both scenarios. So we decided on which trends to fit based on what we thought was physically going on. Before you fit the magnetic field though, you need to take into account Earth's ionosphere. So the ionosphere is has a magnetic field, and so as the pulsar light comes through, it's going to get this extra little rotation as it comes to the GBT. And so in order to probe the magnetic field of the galaxy, you need to remove this contribution. It's not huge, it's just a couple of radians per meter squared, but it's still going to make a difference. So we took this INX code that takes into account things like the time of day, the telescope location, and the line of sight to the pulsar, and it outputs the ionospheric contribution. And so we just subtracted that from the RM and then divided it by the DM, multiplied it by the factor, and we're able to get the magnetic field. So what we found was not anything huge. We did find a couple of trends. We found some sinusoidal trends, and 3 showed periods of about a year, which would point to magnetized clumps along our line of sight. We also found some linear trends, but when we calculated the magnetic field that the pulsar must have gone through in the time between the time that we started the observations and the last day of the observations, it was really big. And so we thought that this magnetic field couldn't be due only to the pulsar's motion throughout the sky. There had to be some magnetic clumps that we weren't expecting. We got a little bonus science out of this, which was pretty cool. One thing that we did when we were looking at the data was we did an outlier analysis. So any RMs that were a lot bigger, a lot smaller, we took out, it was a 3 sigma cutoff, but that would just indicate that on some day there was something going wrong with the telescope or something. So we found an RM and a DM outlier on the same day for J1614 when it was super close to the sun. So there was an angle of about 1.3 degrees between the pulsar and the sun. This diagram is not to scale, but it came within about 4.5 solar radii. And so if you just use the RM or the DM, you find that the magnetic field is about 12 milligauss, which matches the predictions in the literature. So we did a little bit of solar calculation based on the rotation measure and the dispersion measure. So lastly, indications for pulsar timing. That's what we do in NANOGrav. We look at the times of arrival of these very stable millisecond pulsars and search them for gravitational waves. And so these times of arrival are crucial in our overall science goals. And in his thesis, Axel Rogers did robust polarization calibration and showed that there was an increase, that there was an improvement of about 0.5% to about 17% of the residuals in some pulsars. And so that's a huge improvement. And it showed that proper polarization calibration, very robust like we've been doing, could make a big difference in the NANOGrav data and for our TOAs. And so my next project, the one that I'm currently working on, is putting my polarization calibrated data through the NANOGrav pipeline and trying to see how much of a difference it makes. So in conclusion, the data set produced very high signal to noise profiles. It supports the idea that millisecond pulsars are different from canonical pulsars in terms of emission because it comes from a very large region and the polarization angle is much more complicated. The ambient magnetic fields that we find can't totally be due to a pulsar's motion, which we found in the linear trends. There must be some clumps that we're not taking into account, and robust polarization calibration will help our timing in the future. So this data is all publicly available at data.nanograv.org, all of the calibrated profiles in case you want to look at them. Just a quick plug for my science. So I love pulsar science and I love communicating pulsar science. If you want to know more, follow me on Twitter. I do Pulsar Friday basically every Friday. Sometimes I'll highlight a telescope or somebody cool in NANOGrav or talk about a subject. In this picture over on the left, I did a thread on what's inside a pulsar, which happens to be nuclear pasta, which was really fun. I also do science communication with my blog, which is combining Pulsar science and Great British Baking Show. And so I bake something and talk about Pulsar science. You're also free to send me an email if you want to know any more about this stuff. I didn't have a ton of time to go into the detail that I would have liked, but absolutely feel free to ask questions or send me an email on anything. So thank you. I will take any questions that you have.
Thanks very much, Haley. Please submit questions in the lower right, and I see on the Q&A, and I see that a couple have already come in. Would you expect to see from a pulsar with circularly polarized emission an alternating handedness of rotation between the consecutive pulses if each pulse originates from the opposite beam and thus magnetic polarities?
I am not quite sure. That's a really good question. I know that we do see, I don't look at the individual pulses, I just look at the pulsars in just the composite profiles that are made up of lots of observations. I'm not looking at single pulses, but there is change of handedness sometimes in the pulsar profile itself, but that's a very interesting question about the beams, and I'm not quite sure about the answer. I'll have to look that one up.
Yeah, alternate pulses might be different. Very interesting. Here's another question. Could you learn anything interesting about Jupiter's magnetic field by observing a well-studied pulsar when it appears close to Jupiter in the sky?
That's a great question. I am not quite sure. I know that Jupiter does have a magnetic field, but I'm not exactly sure how strong it is. And I'm not sure if the polarization would change. Yeah, I'm not exactly sure, but that's a really good question. I'm definitely going to look into that.
Yeah, that follows along from using the pulsars to probe the solar magnetic field. Yes. I had a question and about the difference in the polarization pattern of slow pulsars and millisecond pulsars. And you basically said you didn't see the frequency dependence in the millisecond pulsars, and then said something about it, the emission arising not in a cone, but in a blob.
We're not quite sure about that. I mean, it definitely goes in a cone because you definitely have this, but it could come, the beams on millisecond pulsars could possibly be wider just because we're seeing emission from a big area. For instance, I'm not quite sure if this is an impulse or exactly what it is, but just the, like, how do you explain this based on one cone? We're not 100% sure. So just, we think that the beams are just wider, but we're not exactly sure.
Mm-hmm. Okay. Any other questions? I don't see any other questions at this time. And so I'd like to thank you very much, Haley, for a most interesting talk. I'd like to remind everyone that these talks are recorded and you should be able to get to them on our website within just a few days. Our next talk will be on 2 weeks from today in January. Jorge Pineda talking about observations of molecular clouds. And we look forward to seeing you again then. Thanks very much for attending.